In this section, we're going to go back to enthalpy, and this is similar to what we've talked about in the past, but different. We did average bond enthalpy, which is a little bit different. It doesn't care about the state of the matter. All it cares about is the bonds that are associated with the enthalpy. This is a little bit different. So this is heat of formation. So if you took all the pieces, parts of a compound and you put them together, this is the amount of heat that would be lost or gained during the formation of this compound. Now, we're going to talk about standard state. If you've watched my other video, I mentioned about standard state. It is typically 298 Kelvin, and if it's a gas, it's 1 atmosphere. If it's a liquid, it's 1 molarity. So notice it has a subscript of F. That lets you know that we're talking about enthalpy of formation. Okay, so in this situation here, we have the pieces parts of methanol. And for my organic chemistry students, notice there's 1 carbon there. Um, we have to pay attention to stoichiometry. Now, you're probably like, why is there a half coefficient in front of oxygen? O2 is the most natural state of oxygen, and we only need one. So we have to place a half in front of it because with enthalpy of formation, we're talking about 1 mole of a substance. We're not talking about multiple moles of a substance. Now notice that it's a negative 201 kilojoules per mole. So this is an exothermic reaction. And you have to pay attention to states. Notice that this is in the gaseous form. We actually probably would be more familiar with the liquid form of methanol because that typically is what it is at room temperature. Okay, so here is a list of enthalpy formation tables. You need this to solve these kind of problems. You can't calculate this without having some kind of table. Now notice that these are all elements in their natural state. They are given an enthalpy of formation of 0 because we can't create these elements. They've already been created. Now, I would pay attention to the fact that the solids tend to be monoatomic, whereas the nonmetals, some of them are diatomic, and you have to remember the diatomics. Don't forget the lucky 7. If you're not sure what the lucky 7 is, could you ask me? Okay, so setting up a calculation for enthalpy of formation, notice that you're looking at heat of reaction, and this little degree symbol represents the standard state. You have to pay attention to the stoichiometry when you're doing these kind of calculations. So it's always products minus reactants. And here's an example here where we have iron 3 oxide reacting with aluminum, and this produces iron plus aluminum oxide. Notice it's a thermite reaction. It's pretty vigorous, very exothermic. Now, when they did this, because there's a 2 in front of iron, they have to put a 2 in front of the enthalpy of formation for iron. And by the way, if it's elemental iron, this essentially becomes 0, which is right down here. And then we have aluminum oxide, which has a coefficient of 1. And we have to look on the table for that enthalpy of formation. And then aluminum. Aluminum has a 2 here, but its elemental state is aluminum, which is 0. And then there's an understood 1 in front of iron 3 oxide. So when you do the math, you get a negative 854.3 kilojoules per mole. Okay, so in this situation here, they've got hydrogen sulfide plus oxygen yields sulfur dioxide and water. So you would have to go to the table to figure that out. Now, obviously, oxygen, you should know right away, oh, that's going to be 0 because that's in its elemental form. Now, when you do look up water, make sure you look up in the gaseous state. You do not want to pick the term that's for the liquid state because that would have a different enthalpy value. And if you were to do the math, so notice that I'm sorry, there's a 2 in front of SO2, there's a 2 in front of water, but water we know is in the gaseous state. And obviously there's a 2 in front of hydrogen sulfide and a 3 in front of oxygen. And we know oxygen has to be 0. So when you do the math, it calculates up to be 1036.8 kilojoules per mole. Now, this enthalpy formation, the reason why this is shown is just to give you a little background. Gold is very unlikely to oxidize or combine with oxygen. And notice that it's a positive heat of formation, so it is not a spontaneous process. But notice that iron, which readily combines with oxygen, is a negative heat of formation. That is a spontaneous process. Um, the numbers here just show you that it obviously was very easy for humans to figure out how to burn wood hot enough so that they could isolate gold by itself. But to actually do it with iron was a lot harder. It took a longer time to figure out how to make heat high enough to figure out how to isolate iron. Okay, so here is an example where we can use different equations to figure out the overall equation for combining carbon and iron 3 oxide. So notice that they have their individual heats of formation. Now, we're going to double reaction 1, and then we're going to triple reaction 2 so that we can have a balanced chemical equation. And notice when you do that, you get a positive enthalpy. This kind of tells you that it's not a spontaneous reaction and it would take a lot of energy to help generate iron by itself using this method. Okay, now with stoichiometry, they could ask you, and this you might see on your exam, where they give you a mass of a substance and you have to figure out how much energy is released or absorbed from that reaction. So notice that they take the mass of the compound and they change it into moles, and they multiply it by the enthalpy, but you have to use stoichiometry to make sure that you get the correct amount for that substance. So you need a balanced chemical equation and you need the molar mass of that substance.